Hello everyone, I'm Yogini Mam, data science trainer at SevenMentor. Like you might be wondering why statistics is important in data science, right? Statistics is so complicated, only maths, probability and all these things. But you know a magic? Just think if you can see the data visually, right? Always we think data means rows and columns, etc. Right? Yes, that is true, rows and columns. But we can actually see the data points, or whatever the values is there in the whole data set. That's the reason statistics is widely used in data science. Whenever we see data, what comes into the mind? The facts, figures, information, etc. Right? So today I am going to give you some tips, some easy methods to understand statistics in data science, the hidden power of statistics. Okay, so let's start with it. Okay, so today's agenda will be data and its types. Okay, demand for statistics, as just now I gave a short introduction about it. Okay, types of statistics, descriptive and inferential. Applications of it will be machine learning models, EDA, deep learning, etc. Also, while explaining these topics, I'll be taking a short data set and explaining the respective topics, and at the last, we will be taking a data set of Bangalore traffic. Okay, so we will able to understand how statistics is very important in data science, and further how prediction can be done on the basis of our statistics. Okay, so let's start. Okay, so as I said before, data is nothing, figures, facts, okay, or any kind of information. Okay, so data can be of two types, qualitative and quantitative. Okay, qualitative, we can say, in fact I'll just tell you how easy to understand qualitative. It only has alphabets. Okay, it will only have alphabets like fruits, apples. Okay, there are no numbers. Yes, we can add numbers, 30 apples, 40 bananas, etc. But then basic name, banana, apple. So these are the categorical values. Further, this categorical data is divided into two types here, ordinal and nominal. Ordinal means here the rank is given for the specific data. So let's consider a student comes first, right? A student comes 10th. So what is this? This is the rank given to each and every child. So this category also falls under qualitative categorical ordinal. Okay. Next, here we have the nominal data. Nominal data, it doesn't give any preference or any order or any kind of rank. It gives only the values, only the categorical values. Here we can see male, female, okay, name of the fruits, name of the people, etc., name of place, country, okay. These all fall under nominal, okay. So let's move to the quantitative part. As we can see, I have written here numerical. The name itself, numerical, tells that it may consist of numbers. Yes, you're right. It is related to numbers only. I'll give you a small hint, okay, for the discrete and continuous. Discrete and continuous sounds very heavy words, okay. So, simple concept with discrete, it only consists of integers. You might have learned this in the standard 6th, right? Integers have negative values, 0 and positive values, correct? So, all the integers fall under this discrete, okay, in this discrete category. Also, we have one more concept in maths, decimals, okay. We do have decimals. Yes, you guessed it correct. Yes, that falls under continuous. Means height can be 5.2, right? Weight can be 70.8, right? These are continuous. This fall under continuous. Here you can have infinite data. Here the data is finite. In still precise way, I would conclude in this way. Okay, so just now I gave you the gist, a small gist of data. What is data? Two types of data, how they are further classified. The reason I'm telling you, we will be requiring this ordinal, nominal, discrete and continuous. These all different types of data in our analysis, statistical analysis. Okay, so that's the reason we just understood what's the data. Let's move next. Okay, in first slide, you might have seen I've written here descriptive statistics. In bracket I've written present and past, right? And inferential statistics. In bracket I've written future. I'll give you a small hint. Descriptive is completely about past and present data. What happened 3 years before? Stock market. Is it about the future? No. What happened in last 60 days or the last day of the stock market is Friday, right? So the closing price is calculated at the end of the day, not at the starting of the day. So the data, descriptive statistics works on the past and present data purely. Okay, inferential data predicts, or it gives the probability, gives the outcome based on the analysis done in the descriptive statistics. Okay, clear with these 2 points? So let's start first with descriptive statistics. What happened in past or what is in present? This is told by descriptive statistics. Yes, descriptive statistics doesn't predict anything. It doesn't predict anything. It only summarizes. It explains you what there is in data, which columns are related, which rows are related to each other, which columns are responsible for the output. Okay, this we already know. The reason I'm telling this, we already know. We sometimes know, okay, the data is from stock market. Okay, so there will be opening price, closing price, high, low, etc. So we might be knowing some of the columns from some of the data, correct? So that's the reason here I've written here what we already know. Still, we need to analyze the data in completely detail if we want to build a model and ask the model to predict. Okay, so here are the few measurable keys. Okay, central tendency, dispersion, position, shape, relationship, and data visualization. We will be going through this and one by one. Okay, so let's start with central tendency. Yes, in from 8th standard, I suppose, we have studied mean, mode, and median, correct? We have studied these topics. We solved a number of problems. We plotted the graphs also, right? There were some bar graphs, okay? Some line plots we have done like this. We had X here and we had Y here. So we drew a line like this, okay? Or we had the bar for population, bar plot for population, right? So we had the range here. Same things are done in statics for any kind of data sets. Okay, so it is not so difficult or it is not a new subject. Yes, it is a bit in different way, we can say. Statics is introduced in data science in a different way, but the original concept remains the same. Okay, so let's start with mean. Mean means addition of all the values divided by the total number of values, right? So addition of all the values divided by total number of values. So that will be n here, correct? Mean is of 3 types: harmonic mean, arithmetic mean, geometric mean. Okay, whatever we use the mean frequently, or we just calculate, okay, someone asks us what is the mean of this data set, we just calculate it immediately. So that time we use arithmetic mean. We use arithmetic, and it is very widely used mean. Harmonic mean and geometric mean, they are used in special cases. Special cases, for geometric mean, I would like to give an example of investment calculations there, and for population also the geometric mean is used. Just a small calculation I would like to introduce in geometric mean. It is very complicated. How? Let's take some data points, x1, x2, x3. Okay, so what the procedure is, first you need to multiply these data points with each other. x1 into x2 into x3. Sorry, here x3. Okay, you might get some value xn. Okay, so you have to take the root of this value. Which root should be here? It should be the number of data points. If the number of data points here is m, in this case is 3, so 3 will come. If m is 10, the value will go to 10. You can understand what is the complication, right? It is not so easy for us. Then think about the machine, right? It's not so easy. So this gives us the geometric mean, and it is very complicated. So they are used only in special cases. Okay, so let's go with harmonic mean. Okay, harmonic mean, it is the reciprocal of arithmetic mean. It is the reciprocal of arithmetic mean. Procedure, short procedure, take inverse of, or inverse is also correct, reciprocal, inverse both are same, right? So take inverse of all the data points. Previous data was x1, x2 and x3, correct? So take the reciprocal, take the mean of them, take its mean, right? Understanding how it is complicated. Okay, so take the mean, and again whatever the value, let's consider you get some value 1 upon xn. Okay, then take its reciprocal. Take the reciprocal of 1 upon xn. So this is harmonic mean. This is used in financial sectors, then also in average speed, to calculate average speed, etc. These are the some real-time examples. Okay, fine. So let's move to the next. It's median. Median. The name itself tells middle value, right? We have also calculated middle value during our school days, college days. Very interesting topics. We got many good marks also. Middle value, it gives for a specific column, okay, or specific data, correct? It won't work completely on the whole data set. Otherwise, you have to convert all the categorical values into numerical. See, because data set doesn't always have only numerical values. It has what you can say, some special characters, categorical values, numerical values. So we need to convert it into numerical, and then we can find the median of the data set. Okay, next is mode. Mode is frequently occurring value. Mode is frequently occurring value. There are many types, okay, like 3 types, or basically 3 types. Here it is unimodal, bimodal, trimodal. If it is more than 4, then it falls under multimodal. I'll just give you an example of mode. Let's take a data set 2, 2, 2, 3, 3. Initial data set, I'll take this. Okay. So which is the mode here? Mode is 2. Which category it will fall? It will fall under unimodal. Next, 2, 2, 4, 5, 6, 6. Here how many numbers are repeating? 2 numbers, 2 and 6 with the same frequency. Just remember, when we want more than one mode, or we want to see the frequency should be same, then only it captures it. right? That it is unimodal, bimodal or trimodal. So here the mode will be, we will be having two modes, 2 and 6. Same case with trimodal. Let's take 8, 8, 8, 9, 9, 9, 7, 8. One more, I will take 7, 7, 7 and 10. So 3 values are repeating here, right? 8, 9 and 7 with the same frequency, 3 times. So this will fall under this category. Okay, this will come under bimodal. Multimodal, same 4 values with the same frequency. Okay, clear with this? Okay. So let's see the diagram. Graphically, median is here, mode is here and mean is here. Okay, just a small view. Okay. Okay. Before going to next slide, I would like to take you to the case study. Okay. So what we will be doing here, I'll just zoom this. I'll just zoom this. Okay. So here are the required files which we have already imported. Okay, I've taken a small data set. Let's consider these are the marks of few students, okay, in particular subject. Okay, so I'll run this for you. Okay, this is the data set. Okay, so mean, mode, median. Okay, so let's start with this mean. Here I have calculated the mean of this data set, right? Okay, you can see dot mean is the internal function, okay, that is found in statics. Okay, let's run this. Okay, so here you can see geometric mean, okay, 56, harmonic mean 56, arithmetic mean is also 56. You might be thinking these all are same, correct? But here the data set is very small, okay, but on large data sets, large rows, the geometric mean, harmonic mean, they won't be same. Okay, they are quite different, okay, from the arithmetic mean. Mode is 54, so we can see here 1, 2, 3. Yes, it is repeating 3 times. So the mode is 54 and the median is 57. Yes, we can see here. Okay. Yes, so let's get back to next measurement. Okay, in central tendency, we saw mean, mode, median. They give us only a single value. But what if we want to visualize the data, the whole data, and we want to understand which are the factors that are affecting the data to give the certain outcome? So in that case, dispersion comes into the picture. Dispersion is nothing but it is the spread of the data point, like this. How the data is spread overall. Okay, so first we need to calculate the range. We know the basic formula of range, right? Max minus mean of any data set. Okay, variance we'll just have a look later on. Okay, standard deviation. Standard deviation, it is the dispersion of a set or data points relative to their mean. Okay, means I'll just show you the diagram here. Standard deviation, yes, we have the diagram here. This is the standard deviation. We have few points here. I'll explain here. That would be much better. The image is very small there. Okay, see, this is my mean. This is my mean, or mu. We call it as mu. Correct. Few data points or maximum data points are around mean, and few of them are away from the mean. So what is the distance between the mean and the respective data points? That is standard deviation. Okay, the concept of low and high, I'll tell you. You can see the more number of data points are around mean, surrounded by the mean. Okay, so the deviation here is low. Okay, because the distance will be low, right? Between the data points and the mean, the distance will be low. You can see few data points here in this area. See the distance, it is very large. So the deviation here is high. Okay, the deviation here is high. Okay, clear. Okay, once we have understood this standard deviation, variance and mean absolute. I'll just clear this drawings. Okay, variation is nothing but the square. Okay, average square deviation from mean. So square of average. Let's consider x1, x2, x3 are our data points. Mu minus x1 the whole square plus mu minus x2 the whole square plus mu minus x3 the whole square. Okay, divided by number of data points, right? In this case it is 3 here. So this is variance, and mean absolute is mu minus x1 plus mu minus x2 plus mu minus x3 the whole upon 3. I'll directly write 3. Okay, now we have understood we have 3 data points. Okay, so to eliminate the negative values, we use squared or absolute. Okay, we have already learned in our previous classes absolute of minus 4 is 4, right? So recalling all these things, yes. So simple terms are used in statics. There is nothing to get afraid about statics. Oh, it is so vast, it is so deep. So basics of our 8th, 9th and 10th concepts are being used, implemented in data science. Just we are at a higher level, so we think, oh, it is very difficult. Just if we brush up only our school syllabus also, we'll be able to understand like how statics is beautiful and very easy. Okay, to view the data in data science. Okay, so clear with this? Coefficient of variance. Coefficient of variance, the standard deviation is proportional to mean. That's it. Okay, we'll just have a look at our code. Okay, dispersion code. Okay, here the data set remains the same. Okay, so this is the inbuilt function I have used, max minus min. I'll just zoom this. Yes, now the view is good. Okay, so variance, these I have used the inbuilt function var for standard deviation, STD. Okay, and the values here we can see the range is 6. Yes, 6 the range, right? Difference between 60 minus 54, what is the difference? Yes, it is 4. Okay. This same calculation is implemented in larger data sets also. Okay, variance is 4.5 and deviation is 2.1. so deviation, how we can understand that each point or the minimum point that is deviated from mean is 2.1. Okay, yes, so clear with this? Let's move to the next measurement, shape. You might have seen there are sometimes like this, sometimes like this, right? Some different types of, sorry, my drawing is very bad. Okay, so just understand. I just want to show a drag of distribution this way. Okay, so here sometimes we see the data scattered like this or biased like this. So those concepts are called skewness and kurtosis. What is skewness? Quantifies whether data is more spread on one side of mean. As we know, mean is very important concept. Okay, I'll just show you the diagram here. We do have a diagram here. Okay, so you can see this distribution. Correct? Let's assume here are the data points. So more number of data points, maximum data points always are around mean, correct? But there are few data points which are very extreme or which have very extreme values and which drag this distribution towards left. In this case, it is left. Okay. So in this case, the mean gets shift. See, because of few values, the mean gets shifted here. The median also gets shifted here, and the mode. Okay. So in this case, mean is less than the median is less than the mode. Mean becomes smaller because it is tending towards the extra or extreme values. Okay. So this is known as negative skewness. This is known as negative skewness. Same scenario this side, you can see here. This is our actual normal distribution, but due to some points, the distribution is dragged towards right side, and maximum data points are towards or around the center. Okay, around the mean. Okay, so here mean is greater than median is greater than mode. Okay, mean is higher. I would like to give example for this in income distribution. Okay, there are few billionaires, right, because of whom the income gets shifted. So does it mean that the mean will be very high in this case? No. Why? Because the majority of income of the people lies near to this mean. So we can't say near to this mean. Okay. So we can't say like this. Okay. That's why the income distribution is very good example of this. And the example, I would like to tell the name here is positive skewness. Positive skewness. Okay. Here the example would be the marks in exam. The marks in exam. Okay. So many of the students are above 40, 45, correct? But there would be some 4 to 5 students who will be scoring very less than 30 marks. Students scoring less than 30 marks, correct? Less than 30 marks students are scoring, correct? So because of their score, the distribution is tracked towards the negative edge, negative side, towards the left side. Okay, so negative skewness. The third one is our favorite, normal distribution with zero skewness. Okay, so the data is properly spread. This is our mean and it is very nicely spread. Okay, so this is with zero skewness. Clear? To understand how much data lies in the tail or in the peak, I mean to say in this peak or in this tail, kurtosis concept is introduced. Measure of how much data lies in tail is compared to the normal distribution. Okay, so here we can see kurtosis. You can see here different types. If the kurtosis, if the value of kurtosis, we will see just in our sample data set what is the value of the kurtosis. Okay, if kurtosis is greater than 3, then it is positive kurtosis, leptokurtic. We called it as leptokurtic. If kurtosis is less than 3, it falls under platykurtic, negative kurtosis. Okay, we can say less than 0, then only we will get negative values, correct? So it will fall in negative kurtosis. And if kurtosis is equal to 0, then it is our normal distribution. Here in this case, yeah. Okay, so how much data point is there? That kurtosis will be giving us these value. Just we will have a look at our code so that you will get a clear idea. Okay, see, this is the shape. We need to import stats library here. Okay, then we can get skew and kurtosis. For our data set, I will run this for you. See, the value of skewness is 0.19. We can approximately say 0.2. So it is positive, right? The skewness is positive. So any guesses where it will lie? Positive means this side, right? So it is, so our data set will be looking somewhere like this. A little bit drag because only 0.2 is there, correct? Okay, and kurtosis, yes, we got the kurtosis negative. Wow, we have the live example here. Okay, so our data set falls in this negative kurtosis. So our data set will be looking like this, see, something like this. Okay, clear with this point? Okay, so let's move to the next. Relationship. Relationship, all the data points are related each other, and they are the dependent variables or dependent features for the outcome. So how they are interrelated with each other? What is the relation between them? The relation measurement tells. The relation measurement tells. Okay, relationship means association between two or more variables. Covariance, it is the consistent pattern of change between variables. Two variables change. If one variable changes, the other variable also changes. So what is the pattern between them? Linear, non-linear, whatever, etc. So we need to understand. So that concept is known as covariance. That concept is known as covariance. Correlation. Correlation, it describes the strength and direction of the linear relationship between two variables. Strength and direction, positive direction, negative direction, upward, downward, etc. Okay, so the types of correlation is positive correlation and negative correlation. Non-linear is also there. Positive means directly proportional, means if suppose x1 increases, y also increases. Okay, this is our independent variable and this is our dependent variable. Why y is dependent variable? Because if x changes, y also changes. So x is dependent on, y is dependent on x1. Okay, so this is one scenario. If x1 increases, y decreases. Okay, so that comes under negative correlation or indirectly proportional. There is one more concept, non-linear. Okay, there is no relationship. Okay, non-linear, it gives you the curve, and there is no relation concept where all the data points are scattered, because few of the columns may not be responsible for the output label y. Okay, yes, I would like to tell you one thing. Correlation term is very important when we do the EDA part. Okay, EDA part for machine learning models. Here let's consider whatever the data set, the examples I took, they only had 3 columns, right? x1, x2, x3. But in real life, it is not like that. We may have n number of columns. Here I'll show, for example, x1, x2, x3, x4 and x5. And this is our y, output label. Okay, so let's consider x1, x3 and x4. Okay, these are responsible for the output label y. We will see this in our example, how this actually works. If x2 is not responsible that much, okay, then we can drop this x2 column. In real life data sets, the columns are more, sometimes 80, 90. So if we try to build a model based on these 80, 90 columns, the CPU will take more time to build, and also the model will become very heavy. So this increases the cost also, right? So in order to reduce the columns, only take the important features or important columns and try to build the y label. In that case, correlation is very important. Okay, clear with this? Okay, so let's go to next slide. This correlation I will tell you, I'll show you in fact in our Bangalore traffic data set. There it will be very nicely visible. Okay, yes, position. In a class, the student stands first, second, some students third, fourth. Okay, so these are the positions where each student is standing in the class. Okay, likewise for syllabus, in running race also, three ranks are given, first, second, third. So accordingly they stand on that dais, correct? Same things are, we can say, they can be correlated in the data set, okay, using statics. Okay, so what does position do? Tell us where values stand in relation to others. Okay, this can be done by using percentiles. Just now I told you the example. Let's consider a boy gets 70%. Okay, 90%. So he is 90% above as compared to the whole class. Clear? He has secured 90% marks above the whole class. Okay, more than the class. Okay, simple to understand. This is same as percentages which we get, but percentiles, it tells you one more thing, that remaining class is below this 90%. Okay, remaining class is below this 90%. Okay, next, quartiles. Quartiles, the name itself, quarters, right? It divides the data set into 4 quarters. So this is the diagram. Okay, let's consider this is the mean. Okay, this is the mean and this is the max of data set. Okay, let's divide this whole data set into half. This is our median. We will name it as Q2. I'll tell you why we name it as Q2, why not Q1. Okay, Q2. This is 50th percentile because it is dividing the whole data set into half. Here we get 50 percentile and here 50 percentile. Clear, right? So I'll just erase this off. I don't want this. Just a minute. This 50% because I need to write something else here. Okay. So clear? Okay. Now let's divide this half and this minimum value. Okay, the first half into one more half. So we will be getting here Q1. That's the reason I didn't name here Q2, I named here Q1. This is the 25th percentile. This is Q1, this is Q2. Then we will divide the next half, that is max minus Q2 again. Okay, and this will be our Q3. Okay, so mostly maximum data should lie between the range Q1 to Q3. That is called as interquartile range. Very famous topic and students get scared about this. There is nothing to scare. See, simple. We take big data set, divide it into half, that is Q2. Again divide the first half into again half, we got Q1, and again divide the second half into one more half, we get Q3. Simple, that's it. While reading, we need to read like this. 25% of data falls below Q1, 50%, 25 plus 25, 50% data falls below Q2, 75%, add this 25% also, 75% time data falls below Q3, okay, and 100% data falls below Q4, okay, Q4, that is understood, okay. Yes, it is found that maximum data should lie between Q1 and Q3, okay. If there is some data outside higher than Q3 or lower than Q1, then they are supposed to be the outliers. Yes, I would like to tell one thing in skewness. Yes, skewness and kurtosis. Here, the tailness and the peakness, okay, means in kurtosis, here and here. They are very important terms to detect the outliers, okay. Outliers are the extreme values which may change the mean, mode, median of the respective data set, and they are responsible for the wrong prediction or some different prediction at the Y label, okay. So that's the reason skewness and kurtosis is very important, okay. So quartiles are also used to detect the outliers, the extreme values from the data set. See, it's better to avoid those values instead of taking them and again building the model, because just because of few values we can't make the model behave like differently, which is expected. If it doesn't behave accordingly, then there will be a problem. Okay, the model will be predicting, it will be biased. We can say it as biased model. Okay, yes. So done with quartiles. One more term is there, deciles. We just divided the quartiles into 4, right? So deciles are divided into 10 parts. The whole data set is divided into 10 parts. D1, D2, D3, 4, 5, 6, 7, 8, 9. Okay, so how many? 9, 10. Okay, so here we can get the exact value. Let's take the example of income distribution. Okay, if I want in which income distribution does 25k fall, 50k fall, 1 lakh, okay, 56k, in which range they fall. So this decile, it helps us to explain. We can just imagine deciles as the step. Okay, so I'll give you a nice example. A girl is standing here, okay, at the first step, and another girl is standing at the third step, and one boy is standing here. Okay, right? So if I want to convey a message to the girl standing here, so how would I tell someone? I would tell the girl who is standing on the step third step, please convey her the message. In same way, this distribution can be seen in deciles. Okay, clear? Simple concepts. The name are quite heavy, right? Something, oh, it's very big, something different, but it's very easy, not to worry. Okay, the favorite topic of all the interviews. What is Z-score? You know, Z-score, it is the very easiest topic than these percentiles, quartiles, deciles. Z-score tells you the difference or how far is the particular data point from the mean. That's it. Simple. Yes, I'll show you like this. Let's take this as, okay, I have this here. I will take only 3 points, okay? It is easy to explain. What is the value of this point? This is Z-score. That's it. From the mean. Okay, what is the value of this? That is Z-score. Okay, so let's have a small calculation for this. I'll explain you. I have a data set 65, 75, 85, 95, 105. Okay, this is my data set. I'll name it as DF. Okay, what my distribution look like? As 85 is my mean, 85, 95, 105, 75, 65. Clear? Okay, this is my normal distribution. This is my normal distribution. Okay, if I want to find, I'll give a point here, 70. If I want to find how much data lies, how much data lies above 70, so we will be using the Z-score. We'll be taking the help of Z-score table also here. Okay, so first this normal distribution will be converted to standard normal distribution. I'll show you here. Means what is the requirement? Mu is equal to 0, correct? Mu is equal to 0 and standard deviation is expected to be 1, correct? So 0, minus 1, plus 1, plus 2, minus 1, minus 2. Okay, so which point we have here? 70, so it will be minus 1.5. Agree? Clear? So I'll just make a line here. This is the mean. I'll take another color so that I can differentiate what we need to exactly find. We need to find this whole area. Okay, we need to find this whole area. Okay, but which values we have. We need to know that also, right? See, as this is the mean, 50% data here and 50% data. Wait, I'll just shade this off, the yellow part. Okay, I'll tell you the reason why I shaded that yellow. I'll take black color, that is much better. Okay, see, this is 50% and this is also 50%. Agree? Clear? Okay, so this whole value is 50%. So we can do a calculation here. 100 is equal to 50 plus 50, right? 50%, 50%. But this 50 we will write as it is. This we know 1.5. We will just check the value from the Z-score table. It is available on Google. Okay, so we'll just look. But what about this yellow shaded? We don't know. So let this be X. So X plus, as this value is negative, we will be referring the negative Z-score table. Okay. So I will just show you Z-score table, negative Z-score table. Okay, so let's see. Yes, see, negative Z-score, view as, I don't want to view. Okay, see, negative Z-score table. Agree? Here we have the value. Which value we had? Yes, it is 1.5, negative 1.5. Can you see here? Right? It is not letting me to do the changes. Okay, no problem. You can see here. I'll just zoom this. Okay, 1.5 and 0. So what is the value? 0.0668. So we will just note this down. The value here is Z-score value is of minus 1.5 is, minus 1.5, 0.0668. Agree? If we convert it into percentage, it will be 6.68%. So we can write here, because all these terms are in percentages, right? And it is making 100%. 6.68%. Clear? So let's add this. Sorry, here it is not 100. It is 100 here. Okay, 56.68 plus X. Clear? So what is the value approximately? 100 minus 56.68. So what the value comes out to be? It will be something 2, 3, again 3 and some 4. Right, yeah, 43.34. So which value is this? Yes, this is this value. We just only found 43.32. Only this much we have found till now. But we need to find the whole region above 70. Okay, so I'll just erase this off. Okay, now this was a diagram. Okay, clear? 0, minus 1, minus 2, plus 1, plus 2. Okay, and our point was here. So we need to find this whole region. Okay, so we got the value, this is 43.32. So let's add, we know this is 50%. Okay, so 50 plus 43.32, it will give us 93.32%. So how much data lies above 70? How much data lies above 70? It is 93.32%. Clear? Okay, easy to understand. That is not so difficult. It is so easy. See, here two things we are getting. The value of our point which we are supposed to calculate, above which the data is to be found. We found this from Z-score table. So this point is deviated 6.68% away from the mean. Okay, clear? Yes. So just we will have a look at our code. Yeah, percentile. Here are the different percentiles. Okay. See, 54, 57 and 58. These are the data which fall under 25, 50 and 75 percentile. Clear? Okay. Clear with the positions. Next measurement, data visualization. As I told you, we plotted the bar graphs, pie charts. Okay, we used to draw a circle, a radius, and we used to just make a groups. and may color it with different colors, right? Very interesting. And also we used to get very good marks for that, free of marks, right? There is no use it was not necessary to use our head or any formulas also. We used to just drew like this pie charts, right, for population and for subjects, right, for all these things. Same concepts are implemented in data science by statistics. Okay, so histogram is used for numerical data, bar chart for categorical data, pie chart also categorical data, scatter plot gives the distribution. Just now I told you no relation, right? No relation concept just now we saw. So that gives us the scatter plot. Okay, and line plot, it gives the trend like this. Okay, like this. Sometimes the peaks are like this also. Actually they are. Okay, so this gives trend over the time. Clear? Okay, these are the few visuals of pie chart, bar chart, scatter plot, line plot, heat maps, histogram. Okay, okay, so we will run the code of that shape of our data visualization. Okay, see, histogram. Our data is like this. Box plot. Yes, box plot also gives us, see, whatever you can see here, whatever you see here, this is the interquartile range. Here is the Q1 and here it is Q3 and this is the Q2, right? Remember the median was 57. Here we can see. Where is it? Yes, see, the median is 57. So that's why the data here is, here we are getting Q2 at 57. If there were outliers, I'll just show you one magic. Wait, I'll add outliers purposefully here. 200. Okay. Okay, I have added an outlier so that we can view. Just don't look at histogram because it will be different only. I want to show the outlier here. Just see. See, can you see the circle? This is the outlier. Is it necessary to capture? Because of one outlier, the whole median will be shifted. I'll show you one more thing. How the median and things are shifted here. See. So, geometric mean, it is shifted here. Mean is again shifted. Mode and median, they remain the same. Okay. If I again change this, let's consider to 500. Okay. Now see the magic. Mean is 93. Is there any requirement? Right? There is no requirement to capture that 500 data point. So we can remove, we have to remove that so that the mean, mode, median won't change to a drastic value. Okay? Clear? Okay. Fine. So this was the data visualization. Okay. Till now, we completed everything about descriptive statistics. Descriptive statistics covers different types of measures on which we conclude or we understand how the data set is actually there. What are the columns related? Which columns are responsible for the output label? Now, coming to the inferential statistics. As in the first slide in agenda, we saw what is inferential statistics. Inferential statistics, it is the future. It will be predicting something based on the past data. So descriptive statistics, whatever we have understood in descriptive statistics, on that basis it will be predicting the respective outcome. Okay, so what is inferential statistics? Makes predictions. Okay, it only makes predictions. This is very important. It doesn't summarize anything in this case based on the decision. Okay, decisions on the data. Okay, this uses only sample to make guess about the whole population. It takes only sample data. Let's consider the exit poll during the elections. Exit poll. Do the election voluntary people go at everyone's house, each and every one house, and ask like who will be winning this time? No, they won't. They just select an area. They randomly ask the people and they conclude accordingly. Okay, so this time this party will be getting more votes. A party will be getting more votes or B party will be getting the more votes, right? So in this way, we won't be taking the whole population. We will be taking only the sample of it for predicting purpose, and on those predictions, we can say the population will be acting in same way. It may predict in same way also. Okay. Yes. What is the need of statistics? Just now I told entire population can't be taken. Okay. Help in decision making for like we can see examples during launching of a new product, right? Launching of a new product. There some decisions, the previous market decisions may help us to launch a product, correct? Okay. Uses probability and statistics. Inferential statistics uses inferential probability to predict the outcome. Okay. Yes. What is probability? Let's start with the probability. How likely an event is to happen. This definition was done in class 11. Yes, right? Class 11th math subject. Probability, permutation, combination. This was how likely the event is to occur. Rolling of a dice, flipping of a coin, right? Removing a card from a deck, which is like evenly likely. Okay. So the outcome always lies between 0 and 1. Okay. There are 3 types of probability: theoretical probability, experimental probability, and subjective probability. Theoretical probability based on formulas. Okay. Dice, flipping of a coin. It is calculated dividing favorable outcomes by total number of possible outcomes. Let's consider we have a coin. Okay. A fair coin, not a biased coin. Okay. Heads and tails. Clear? What is the chance of getting head? 1/2. What is the outcome? 1/2. Correct. So here is some formula. Means this is the formula. Dividing favorable outcome, that is head. Okay. By the total number of possible outcomes. What are the possible outcomes? We may get a tail also. So these are the 2 possible outcomes. Clear? Okay. Experimental based on real experiment. Let's consider. I'll clear this. Okay. Let's consider if I toss a coin. Okay. How many times? 100 times. I toss a coin 100 times. What is the probability? Or I can say I may get at least 48 times head. Correct. If I toss 100 times, there is a chance of getting 48 times head. So what is the probability of getting head when coin is tossed 100 times? That is 48 upon 100. 0.48. Clear? So this is, we are tossing the coin again and again to do some experiment and to get respective results. Okay. So this is also known as empirical probability. Clear? Yes. Subjective probability. Based on belief, experiment, or intuition. See, in subjective, there are no experiments, there is no formulas, etc. here. Okay. Here it depends upon, it varies and it depends upon person to person. Some people may have some different intuition about the data set or about the outcome, and they may predict or they may tell accordingly. Okay. So, example, doctors assure 70% chance of recovery. Let a patient is ill, okay, for many days, and the relatives ask, like, doctor, what is the chance of recovery? So he may tell, maybe he may recover 70% or 60% accordingly. He can't assure, he can't say, no, for last 15 days admitted in the hospital, so there is a chance he may recover 30%. No, that won't be the thing, because his body should respond accordingly. Okay, so this is the subjective probability. Okay, and this is used when the data is limited. No formal calculations are there in this. Okay, yes. In inferential statistics, Bayes' theorem is used. What is Bayes' theorem? It is used for calculating conditional probabilities. You know, the Bayes theorem, we have actually used this in class 12. I'll give you a beautiful example, then you will be able to recall. Like, yes, we have actually worked for drawing the cards. The card should be black, the card should be heart, the card should have king. So this is conditional probability. Okay, gives probability of an event based on prior knowledge of conditions. Okay, it has concept of conditional probability. What is conditional probability? Conditional probability of A given that another event B has already occurred, means one event has already occurred and depending on that the another event should happen. Okay, so let's take an example. I'll just clear this off and I'll explain you this beautiful example. Yes, I have 3 boxes here. Just imagine all these 3 are equally drawn. Okay, my drawing is not so good. A, B and C. Here there are different colors of balls. So it is 2 red, here the data is there. Okay, we already have the data. And 3 black. 3 red, 1 black, 1 red, 4 black. Clear? This is, they all are equally likely. The boxes are equally likely. Okay, equally same. So we want to find the probability of getting red ball from box A. I want to get the value or the probability of getting chosen red ball from box A. What is the probability? Okay, so let's start. And just remove this. Okay. Okay, this, just remember what is our requirement. Okay. Okay, let's, so as these boxes are equally, so each box will have the probability of 1 by 3, right? A is equal to 1 by 3, B is equal to 1 by 3 and C is equal to 1 by 3. Clear? Okay. Then we need to find probability of getting, let E be the event of getting red, okay, red ball. Let E be the event. So the event E from A, what is it? 2 by 5, because total number of balls are 5, 2 plus 3. And what is the event of getting red? It is, okay, so why 5? It is 2 plus 3. Total number of balls is 5. Okay. And then what is the event of getting red? There are 2. Okay. So chances of getting red is 2. Same with B. It will be 3 by 4, right? 3 red balls. Yeah, correct. It's 3 red balls. Total number of balls is 5. For C, it will be 1 upon 5. Clear? Okay. Now, we need to find the probability. First, we need to find the probability of getting only red ball first. Then we will go to the probability of getting red ball from box A. Okay. So, meanwhile, the formula here, this is the formula. I've already written because it is quite big. Okay. So, just we will apply the values here. E of A, 2 by 5 into P of A. What is P of A? Probability of getting from box A, 1 upon 3 plus 3 by 4, sorry, into 1 by 3 plus 1, sorry, 1 into 5, oh sorry, 1 by 5 into 1 by 3. Okay, so values 2 upon 15 plus 3 upon 12 plus 1 upon 15. Okay. So what the values will be here? The value comes out approximately to be 0.42. But which value is this? It is only of probability getting red. If we want to get the probability of this from box A, getting the probability of red ball only from box A, then now we have this value as 2 by 3 into probability of A is 1 by 3, the whole of probability 0.4. So this value comes out approximately whatever the value comes out. Okay, so let's assume it is some 0.38. Okay, I have not done the calculations in detail. So probability of getting red ball from box A, this is the answer. Okay, we have already done, if you recall these things, we have already done. This is conditional probability and this is Bayes' theorem. That's it. Okay, interesting. Yes, I have written purposefully this Sherlock Holmes. You remember Sherlock Holmes, the TV serial episode? Okay, or any crime serial. Initially, when the episode starts, some incidents happen and etc. And the culprit we found. We find the culprit. Oh, he's the culprit. Since then, we start to make some intuition. Oh yeah, he did this crime because of this. So for this reason, he's doing this. But after a few scenes, again, our intuition changes accordingly, right? Whatever the predictions we done before, it has been changed. So in same way, the Bayes' theorem works. Okay, so this is our simple Bayes' theorem. Okay, fine. So we will just go through our Bangalore traffic dataset. Very interesting dataset, you know. The dataset is actually very big, but I have just modified it for the demo purpose, for the case study. Okay, these are all the required libraries. Okay, I will just read this dataset into DF. See, area name, different areas are there. Road section name, traffic volume, average speed, time travel index, congestion level, capacity road utilization, incident reports, environmental impact. I'll just zoom this. Okay, traffic signal complaints, parking usage, okay, and weather conditions, pedestrian and cyclist count, road work and construction. Oh my god, so many columns are there just for a traffic data set. So now you can understand why the correlation topic was important. So many columns are there. These are only, I think, few of them, but for traffic there might be still more columns also in real time. Okay, yes. So info, we will check whether all the data, whatever the columns are, they are into integer and floats, because machine only understands integer and float, the numbers. It doesn't understand the string or the categorical format. Okay, so here we see. Okay, here few are objects. Okay, the names: Jayanagar, MG Road, Anil Kumble Circle, Jayanagar 4th block, South End Circle, etc. Okay, so these we need to convert into numerical format in EDA process. Okay, I've converted this date time. This is object. Okay, I've converted into date time. Okay, yes, we have already done. Yes, so describe. What does this describe? See, the mean of traffic volume. Here it is a very big data set. So I'll be just giving you we will be just running off with the experimental theoretical whatever we have done. Experiment, we will on this few of the columns. We will do the experiment on few of these columns. Okay, so for some time I'll be taking traffic volume, for some of them average speed, for some of them an incident report, etc. Anyone, you can also play with this. Okay, this is very beautiful data set. So the mean of traffic volume is 33,391. The standard deviation is this, minimum is this, 25%, 50%, 70%. Describe. Dot describe function actually describes what all there is in the data set. Okay, irrespective of the categorical or what do you say, categorical or numerical format. Okay, yes, yeah. Our topic starts here, arithmetic mean. Okay, arithmetic mean. I have taken the mean of traffic volume. For mean, I have taken the column mean, traffic volume. So I'll be working on this. See, this what single mean we calculated, 33391. Same mean we got here. Agree? Okay. Median. Okay, median. It is. Okay, here it is that. Yeah. So median, what what is the value of median? 34169. So let's check. Median is not seen here. Okay, median and mode are not seen in this describe. So I will run this. Just will check. Yes, the mode. Yes, the multimodal concept has been introduced here. See, these are the number of modes which we are getting in our data set. There are so many number of modes here. Okay, dot mode. These are all the modes. Okay, we are getting. There is not single mode here. Okay. Yes, geometric mean, harmonic mean, they are almost similar because I have taken a small number of data set. Dispersion value range here is 54116. This is for traffic volume. Traffic volume means these many vehicles. Okay, these many vehicles are there. Variance. High variance means data is very spread out around the mean. Data is very much spread around the mean. This is the variance. You remember I showed you, just a minute, I'll take the help of PPT. Yeah, I showed you like this spread. I showed you spread like this. So our data set, current traffic data set is also spread here like this. It is very much spread. Okay. Yes. Standard deviation. 15,175. Okay, on an average each traffic value differs from mean about 15,000 vehicles. So we can understand 50,000 vehicles, the minimum deviation is 50,000 vehicles. Okay, each value differs with 15,000 vehicles from the mean. Okay, yes, our mean was here. Let me check. Yes, it is 33, and the standard deviation we are getting here is 15,175. Okay. Yes. Shape, kurtosis and skew. Yeah, we are getting a normal distribution here. Congratulations, means our data is normally distributed here in this case. And here we can see the kurtosis is again negative. So only a few points they are tending to be in the tail, and they are leading to the negative kurtosis, that is platykurtic. Okay, platykurtic traffic volume is flatter. Okay, and less extreme to a normal curve. Traffic is spread more evenly with fewer white spikes, because see, spikes, you remember the peakness? Yes, this peakness. So it is less peak and more tailedness. So it will be like this. So this and this same, widespread, platykurtic, all the concepts. Okay. Yes. Relationship. Yes, this is the thing where I wanted to show you the importance of correlation. Okay. See, I have taken two columns. I want to check the relation between two columns. We can say two data points here. Okay. Two columns, two features we can say. More technically, two features. Okay. Traffic column and congestion level. See, traffic volume and traffic volume, if they are correlated, of course it is 1. With congestion level it is 0.8. So it is highly related. So related highly or positively relationship. With date, see, it is negative. If traffic is increasing, date is not. So there is no relationship only. Okay. And parking, traffic volume, parking usage. If traffic is more outside, of course the parking usage will be less, right? If traffic increases outside, the parking usage will be less. So they are negative relationship. They have negative relationship. Yes. Percentile 25, 50, 75. These are the vehicles, we can say, number of vehicles fall in this range. Okay. Z score. See, here it has given Z score of each and every value. I will show you the data again. We have 20 data points in this data set. Okay, see, 20 data points and it is showing us the Z score of each and every value. Where it went? Just a second. Yes, traffic volume, Z score of each and every value it is showing. If Z score is 0, value is exactly the mean. If Z score is above, let's consider 1, 2, 3, 4 and many more. Like this, positive are in positive. Okay, so they are above the mean. If it is less than 0, then it is below mean. These negative values, minus 0.74, minus 0.16, minus 1.71, etc. Okay, so these are below mean. If the values are greater than 2 or 3, then it is considered as an outlier. As I told you before also, Z-score is also an important factor to detect the outliers. Okay, very far from the mean. There is no point considering the outliers. Okay, data visualization, the beautiful part of our statistics, where we can see our data so nicely spread, evenly spread, unevenly spread, biased, unbiased, etc. Okay, so I have plotted the graph between average speed and incident report, because small data set easy to understand, right? So see, this is the bar graph against average speed and incident report. Okay, so I'll do one thing. I'll read the data here again so that it is easy for us. Yeah, so I'll read the data again here. Okay, yeah, see. So which columns? Yeah, average speed. Okay, average speed and incident report. Incident report 0, 1, 2, 3, 4, 5 is the maximum value, and average speed we can see 50. I can see 50 is the maximum. 56 is the maximum. Okay, and the minimum I suppose 26. Yes, it's 26. Okay, so we will be seeing here, see, maximum 5 on y-axis and 56 on x-axis. Clear? Okay, yes. This is the histoplot. Histoplot is used, as I told before, it is for categorical data also, and from histoplot we can get the distribution. See, I have shown you the distribution here. I have shown you the distribution, right? This is the histoplot. This is the histoplot, and this is the distribution. How? Yeah, we can get a proof. Yeah, just now we can see kurtosis, where the kurtosis went. Oh yeah, see, you remember I just showed you this diagram. So yes, we are getting exactly here. We can see, same. The data is spread out everywhere, right? Spread over a quite range, big range, from 29 to 56, right? Good, we are getting the proof also. Yes, yes. This is the scatter plot. Scatter plot, different values, pediatric cycle count and average speed. Okay. Okay. So pediatric cycle and count, we have plotted against it, how they are related to each other. Okay, and this is the pie chart of average speed and area. I have given the area, average speed with the respective area. So see, we can see here which area. I think MG road has a higher value here. Let's see, MG road, yes, average speed, no, right? Yes, Hebel has a 56 average speed. Okay, and MG road has 34, 29, 37, 45. These all values are there. Okay, so it has plotted in this way. Whitefield, yes, sorry, it was Hebel only, correct. I didn't see this blue color. So the area Hebel has the more average speed. Okay, yes, clear. So this was all about descriptive statistics and an introduction to inferential statistics. So in next video we will be continuing about the inferential statistics in detail. Okay, so we done with the Bayes theorem. So in today's session we completed complete descriptive statistics like central tendency. We saw the measure of central tendency, dispersion, position. Then in position percentiles we saw, correct. Then we saw the correlation between different data points or different variables, data visualization, etc. So also we saw the introduction of inferential statistics. Okay, inferential statistics, what is probability, Bayes theorem, conditional probability, why probability is important in inferential statistics. This was just an overview of inferential statistics. In next video, we will be seeing more deep into inferential statistics, the topics like hypothesis testing, statistical test, non-parametric test, A/B testing, also the probability distributions. So guys, stay tuned. Bye-bye.